Hello. In the last two lectures, we developed a decoding algorithm for the extended binary Golay code C24. We did some rather tedious calculations to confirm that C24 has better reliability than a comparable binary Hamming code and a comparable binary replication code. We're now ready to begin the second half of the course, beginning with Chapter 5 on cyclic codes. A cyclic code is a linear code that's also closed under the operation of right cyclic shifts. We'll spend some time developing the theory of cyclic codes. We'll eventually use this theory to develop a decoding algorithm for burst error correcting. And we'll also use this theory in Chapter 6 on BCH codes. Chapter 5 on cyclic codes is comprised of 7 video lectures. I'll present cyclic codes in V5a, where we'll characterize cyclic codes as ideals of a certain polynomial ring. These ideals will be studied in V5b. In V5c and V5d, we'll further study cyclic codes and determine the dimension and generator matrix, the dual code, and the parity check matrix of a cyclic code. In V5e, we'll find a nice PCM for a cyclic code and show that computing syndromes with respect to that PCM has a nice algebraic interpretation as polynomial division. We'll exploit this technique for computing syndromes in V5f and V5g, where we'll present a decoding algorithm for cyclic burst error correcting codes. In Chapter 3, we studied linear codes, and we saw several nice consequences of the vector subspace structure that linear codes possess. For example, we saw that the distance of a linear code equals its weight. We also saw that we could represent the code words in the linear code quite compactly using a generator matrix for the code. And this yielded a very efficient encoding algorithm. Perhaps more importantly, we saw that every linear code has a dual code. A generator matrix for the dual code is called a parity check matrix for the code. And the PCM told us a lot about the code itself. For instance, we used a PCM to define a general purpose decoding algorithm for linear codes, which we call syndrome decoding. We saw an infinite family of single error correcting codes called Hamming codes. And we saw the binary Golay code and its extension C24, which has error correcting capability 3. One drawback of linear codes is that it isn't easy in general to determine the distance of a linear code. To tackle this problem, we'll specialize linear codes even further to cyclic codes, which we'll study in Chapter 5. Unfortunately, cyclic codes also have the problem that their distance is difficult to determine in general. So in Chapter 6, we'll specialize cyclic codes even further to BCH codes. We'll see that BCH codes are specially chosen cyclic codes which have a nice lower bound on their error correcting capabilities. Alright, so let me define cyclic codes next. First, a subspace S of our vector space Vn of f is called cyclic if for every vector in S, its right cyclic shift is also in S. So in other words, a cyclic subspace is a linear subspace that is closed under the operation of taking right cyclic shifts. A cyclic code is a cyclic subspace of Vn of f. Cyclic codes are linear codes with the additional structure that for every code word in the code, its right cyclic shift is also a code word. Our next goal is an algebraic characterization of cyclic subspaces of Vn of f as ideals in the ring of polynomials over a field f, modulo x to the n minus 1. This will necessitate the introduction of concepts from the theory of rings and ideals. In this chapter, F will be the Galois field on Q elements, and R will denote the ring of polynomials over F, modulo x to the n minus 1. Recall that the elements of the ring R are all the polynomials of degree less than n having coefficients in F, and we perform multiplication of these polynomials modulo x to the n minus 1. We know that R is a commutative ring, but R isn't a field since the reduction polynomial x to the n minus 1 is not irreducible over F. In fact, x minus 1 is a proper factor. We have this natural bijection between the elements of the vector space of dimension n over F and elements of the polynomial ring R. Namely, a vector A of length n is associated with the polynomial a of x of degree at most n minus 1, whose coefficients are the components of the vector A. This bijection preserves vector addition and scalar multiplication in the following sense. For any two vectors A and B, when you add them together, the addition is component-wise, while if you add the associated polynomials together, the addition is coefficient-wise. So this bijection associates the vector A plus B with the polynomial A of x plus B of x. Similarly, if you multiply a vector A by a scalar lambda, then every component of A is multiplied by lambda. Whereas if you multiply the associated polynomial A of x by lambda, every coefficient of A of x is multiplied by lambda. So the bijection associates the vector lambda A with the polynomial lambda times A of x. In the remainder of this chapter, I'll interchange between vectors and polynomials. So I might call such a vector a polynomial, by which I really mean the associated polynomial, and I might call this polynomial a vector, by which I really mean the associated vector. I can now use this bijection to define a natural multiplication on the vector space. This multiplication will not be the same as the inner product, where the product of two vectors is a scalar. Here, the product of two vectors will be a vector. So let A and B be vectors in the vector space. Then A times B is defined to be the vector C, where the polynomial associated with C is A of x times B of x, modulo x to the n minus 1. Note that this polynomial has degree at most n minus 1. So the vector corresponding to C of x has length n. A question worth asking is, why did we choose this particular degree n polynomial as the modulus for the polynomial ring R? Let me tell you why. So let A be a vector, and let A of x be its associated polynomial in R. Then the product of x and A of x is this polynomial of degree n. In the ring R, we're working modulo x to the n minus 1. So I can divide x to the n by the modulus x to the n minus 1. In other words, just subtract the modulus from x to the n. We see that x to the n is congruent to 1 modulo x to the n minus 1. So when working modulo x to the n minus 1, I can replace the term x to the n by 1. And so this monomial becomes a constant term a n minus 1. The vector associated with this polynomial is this one, which you recognize as the right cyclic shift of the vector A. And so, multiplication by x of a polynomial in R corresponds to a right cyclic shift of the associated vector in Vn of f. For my main result on the algebraic characterization of cyclic subspaces, I'll need the notion of an ideal of a ring. Let R be a finite commutative ring. A non-empty subset, I of the ring, is called an ideal of R if I is closed under addition and I is closed under multiplication by elements in R. So for all elements A and B in the ideal, their sum is also in the ideal. And for all elements A in the ideal and any element B in the ring, the product of A and B is in the ideal. Two trivial examples of ideals are the zero ideal and the ring R itself. You can check that these two sets satisfy the definition of what it means to be an ideal. All right, here's our algebraic characterization of cyclic subspaces of our vector space Vn of f. Let S be a non-empty subset of the vector space, and let I be the set of associated polynomials in the ring R. Then S is a cyclic subspace of Vn of f if and only if I is an ideal of the ring. Let's prove the theorem. For the proof, you'll need to remember the definitions of a vector subspace, a cyclic subspace, and an ideal. So first, suppose that S is a cyclic subspace of Vn of f, and let I be the set of associated polynomials. Since S is non-empty, I is also non-empty. And since S is closed under addition, I is also closed under addition. We next need to show that I is closed under multiplication by elements in the ring R. So let A of x be a polynomial in I, and let B of x be any polynomial in the ring R. Now the vector A associated with A of x belongs to S, and since S is a cyclic subspace, it's closed under right cyclic shifts. And so the associated polynomial of the right cyclic shift of A, which is x times A of x, also belongs to I. Repeating this argument shows that x to the I times A of x belongs to I for all I between 0 and n minus 1. Now, since S is closed under scalar multiplication, if you multiply the vector associated with this polynomial by any scalar, the result is also in S. And this means if you multiply this polynomial by any scalar bi, the result also belongs to I. Finally, S is closed under addition. So when you add the vectors corresponding to these polynomials together, the result is an S. And this means that when you add these polynomials together, their sum is an I. And now you see that the sum is precisely the product of B of x and A of x. So this shows that I is closed under multiplication by elements in R. And hence, I is an ideal of R. Next, we'll prove the converse. So suppose that I is an ideal of the ring, and let S be the associated vectors in the vector space. First, since I is non-empty, S is also non-empty. Secondly, since I is closed under addition, S is also closed under addition. Thirdly, since I is closed under multiplication by all polynomials in R, it's also closed under multiplication by the constant polynomials in R. The constant polynomials being scalars in the field F. And this means that S is closed under scalar multiplication. And so we conclude that S is a subspace of the vector space. Finally, since I is closed under multiplication by all polynomials in R, it's also closed under multiplication by the particular polynomial x. Recall that multiplying a polynomial in R by x corresponds to the right cyclic shift of the vector associated with that polynomial. And so we can conclude that S is closed under right cyclic shifts. Thus, S is a cyclic subspace of the vector space. So we have this nice bijection between ideals of the polynomial ring R and cyclic subspaces of V and of F. To study cyclic subspaces of the vector space, we'll proceed to study ideals of the polynomial ring R.
Now that we have this nice one-to-one correspondence between ideals of the polynomial ring R and cyclic codes of length n over f, we'll spend some time studying ideals in the next lecture. And we'll use this information to learn about the corresponding cyclic codes. We'll see you then.